Okay, so that's copy 2. We'll kill that. All right, hello again. Copy 2 is there. I will call this Inverse Square Lab. And I'm going to open up, oh no, my emails. Don't look at my emails. 09PH, you nerds, there you are. C at Ashad. Could you please open up your laptops? Could you please open up that document that I just sent you? Okay. And I will eventually look at your graphs. I'm sure they're all lovely. Now, we are going to do a little bit of Excel spreadsheeting. I will tidy this up. Some of you might have done this in in computer science, but Microsoft Excel is really, really useful. And the problem is I get year 10s and 11s and 12s that are still sending in tables that look god-awful. It's like they've taken a photo of their screen in the reflection of a mirror and then put it on a third of the page. I want you guys making really, really nice tables in years 9s, 10, 11 and 12. So, have this open. You'll notice I've got the high intensity and the medium intensity, and I've got a couple of charts that they're already made, right? So they're just waiting for the values. What they're going to do, they're going to take, oh, that's the fun one. Let's look at, oh, that's also the fun one. Okay, they're both fun. They're going to inverse the distance and square it, and they're going to put that across the x-axis, and then they're going to take the average relative intensity. Okay, so hands up, who has Excel open with this template? Awesome. Could I get you now copying in your 2 trials for your high intensity and your 2 trials for your low intensity, please? Yeah. And because I'm lazy, here's one I prepared. Yeah, what's up? Oh, you weren't here. Yeah. Ah, well. Just borrow Davey's data. He's good for it. Yeah, right. Well, enable content. Click, there's a little button at the top that says enable content. Alright. No, that's still the same blasting cool. Where is... Ah, there we go. Okay. Okay. Kenneth Lowe, if you're reading this, no, you're listening to this, you should be putting your data into the Excel spreadsheet as well. Okay. Now. Oh, they're working as a team. He's taken his protective case off. How risky. Alright. Oh, that's a lovely inverse square. Very nice. Show me your graph. Show me your graph. Oh, God. Did it. Yeah, 31. Joe mode, well done. What's this? Why are you going that way? We work left to right here. Come on, left to right. Oh, this one. What about your inverse squares? Does not have the line in there. What's this also? Yeah, it doesn't either. Is that square or? Well, maybe. Man, don't go show this. Should be linear, but not too bad. Boom. And 39. Oh, no. Oh, okay, fair enough. R squared. I won't discriminate. Oh, yes, this sounds different, and we have to respect each other. Why is this linear modeling? I did not have a pencil. And stuffed. Oh, so I didn't do the English. That's why you don't. Okay, alright. Is that your data?
Yes.
Cool. Nice. Say, guys, show us. Cool. Nice. Nice. Good. Alright. Okay. Who has entered all of their trial 1, trial 2, trial 1, trial 2? Alright, everybody else, hurry up. Okay? Now, I'm just sort of going along with this. Let's tidy some stuff up. Now, there is a rule. Could you just zoom, enhance? There is a rule that when you multiply or divide, you really want to express your answers to the same sig fig. But look, this pesky Excel is rounding. I measured my distances to more than the nearest 10 centimeters. So could we just pin our little taskbar to the top, so pin the ribbon, right, so it doesn't disappear. We're going to go over to Home and see this button here. It is your friend. Oh, there. Okay. So, and you might have lost a half a mark or one because your data wasn't being expressed to the same decimal. So let's click that. That's a bit nicer. Maybe one more. I reckon we could measure our distance to the nearest millimeter. Now, here, we don't want recurring numbers. We don't want irrational numbers. And then Excel's gone crazy. It's gone, let's round that first one to 0, and then let's just spit out 8 for the next one. No, let's be consistent. Let's go. I think 1 decimal is good enough here. Maybe 2. Let's go 2 decimals. You'll learn these rules more if you do Year 11 physics. Okay? Now, all of these values on the... Are we still struggling? You've got to highlight those cells. Yeah. So click and drag to highlight all the data. And then you can either add decimals or take decimals away. Alright? Now this one's fine. Our lux readings were to the nearest 1, LUX, and so that's all cool. Our averages, maybe we want to express them to the nearest, it doesn't really matter. The numbers are still there, it's just how we display them. So I might just go highlight this, let's just round these bad boys and decrease the decimal. There we go, that's looking nicer. Okay? And that's looking nicer. Okay? Now, next you'll notice I've already made these numbers sit in the middle. So you can see I have center justified them and I've put them in the middle of the cell. You could put them all left justified, but nah, I like things to be nice and in the middle. Okay? Next, you'll notice I've got my label at the top and then the units at the bottom. Let's just put those in brackets. Now, there used to be, when you were in Microsoft, you could highlight that and go Command-Shift plus and it would superscript it, but it doesn't have superscripts. I think you can go into font. If you highlight that too and go into... No, where's font? Draw? Data? Insert text. In symbols? Yeah, so look, if this is going to be your, what's the term? No, you can't insert it. It's not letting me. Text, symbols, equation. Not your Waterloo. No, so that's just going to float anywhere. No, we don't want that. Doesn't matter. So, look, here's what you could do. You could import this into Word, and then you would highlight that too and go Control-Shift plus, and it would bump it up to a superscript. But that's all right. One thing I do like to do, and this is just me personally, I like to shade 30%. Wait, where's that one? Just to make it a little bit, the title's a little bit darker. And then highlight them all, and we're going to go borders. So we're going to go... Where is it? Where's my borders? Insert... No. Draw. No. Oh my gosh. Where's my borders? There it is there. Borders. Sorry. Okay, I got lost. There's our borders. So highlight all your data. Let's go a nice thick outside border. Boom. We might want to separate our headings from our data, so we'll click that again. Nice thick outside borders. And that way, when you copy and paste that, oh, hang on, maybe we could, you know what I'm going to do? Let's highlight, boom. Look at that. That looks a lot nicer. You can just highlight that, copy, paste into Word. Okay? Now we're going to come back and add some columns to this. So I'll show you how to merge and center and wrap text and things like that. But all right, let's just have a looky-see down here. This one has given us a trend line. Let's just zoom out a bit. Let's add a trend line. I don't know why I just sort of gave up when I was making this document. Let's just click on one of the dots over there. In fact, let's right-click and we'll go add trend line. Now, I'm sure you guys all know how to do this. It is definitely linear, okay? But unfortunately, our data looks a little bit logarithmic, a little bit, ooh, not that one. Ooh, no. Ew. It seems to be a square, but it is linear. So let's just go with linear. Okay, and let's put the equation on the chart and display the r squared. Now, have you guys done correlation coefficients in maths? No, okay. All right, so this little r squared value. So if you're still playing catch up, you right click on your data, you go add trend line. You're selecting a linear trend line. Roman, you are showing the equation and the, whatever it said, r squared value. Now, the r squared value is telling you how close your data represents the equation. If it's an r squared value of 1, then it is perfectly correlated. Every single dot of data lies on that linear equation. Well, that never occurs. There's always going to be a little bit of variance, right? Someone walked past the light, and suddenly gave you a little bit of a higher reading, and it increases your data. So, 0.9965 is pretty much a very strong correlation. That we're pretty certain that our data fits a 1 on r squared. Okay? Now, you can, if you want to be cheeky, let's go back to this guy, which doesn't really look very linear. You could change the trend line. Oops, don't click that. Add trend line. You could go polynomial. Oh, I'm going to have to delete one. Now, look at this. It went from 0.996 to 0.9989. So it's actually suggesting that it's not linear, it's actually a quadratic. But I know that it's linear because I'm telling you the equation is the inverse square. There could be a reason for this. With the lower voltage, you had more background light. With the lower voltage set to 6 or 8 volts, you weren't getting as much intensity. So any background light from the whiteboard, or a kid walking past, or the group on the other side of the class turning on their light box and shining a beam of light into your sensor may have affected your data. Okay? So let's just go over here. And I'm just going to see if we might be able to just go control cuts, and then I'm going to open up. Now, you're not going to do this, so just have a look. I'm going to see if I can paste this here. I don't know if I can. It is Microsoft. Oh, lovely. Cool. We're all learning stuff. Woohoo. All right, cool. So, you will probably learn in maths when you are trying to fit trend lines. All right, you're going to look at correlation. And anything above sort of a 0.9, 0.95, you're pretty confident, okay? And in physics, it's either going to be a linear, or a quadratic, or a cubic. Sometimes it's an inverse, sometimes it's an inverse square. This is what we had. This is the inverse square, right? So if we can linearize our y versus 1 on x squared, which is what we've just done, we can pretty much, it supports the idea that the light intensity drops away as per the inverse square. And we will look at, oh look, there's a lovely little graph there. Now, just have a look with your eyeballs onto this page. this is hopefully showing you that all of that light intensity is traveling out spherically from a point source. So we are treating the filament as a point source of light, even though it's a little piece of metal that's horizontal and shining. The sun is a really good example of a point source of light, even though it isn't a point source, but we can treat it as a point source, and all of the energy, as it gets further out, that energy is being spread out of the surface area of a sphere, which has the equation of 4 pi r squared. Now, your intensity at any point is the power divided by the total surface area. So what you have, and you will go to this in just a moment, but I'm just going to write it as watts per square meter. It's how much energy per second passing through a square meter. Now, this diagram shows it very, very nice. If you were to double your distance, then the area has gone up by a factor of 4. So if you double R, you're getting a quarter of the intensity. If you triple R, then the area has now increased to 1/9. So 9 times. So now the intensity is shared over 9 times the area, you're getting 1/9. If we go to R times, then it's spread out over R squared, and you're getting 1 over R squared. So that's what you were measuring. You were basically, I don't know, you were putting your sensor, your light source, your sensors, light source here, and you're putting your sensor there, and then there, and then there. It's getting further and further away. It's getting less and less intensity of light. Now, I just had a quick look. The lux, Lux, it's just an arbitrary unit, but you can get an effective, it will convert. So if I had 100 lux, and it's a halogen lamp, then it's 20 lumens per watt. If we entered the surface area or the spherical radius, I don't really know, you can convert, okay? But what we're going to do is just pretend there is no simple conversion. It depends on a lot of stuff. It depends on your wavelength, the shape of the object, whether the object is a perfect black body, which we learnt about in the previous term. But a rule of thumb, a rule of thumb is we could just pretend that we had a little sun burning there. Incandescence, right? It's jiggling really fast, it's emitting visible wavelength. So is the sun, jiggling really fast, emitting visible wavelength. So, the conversion is 1 lux is 0.00079. Alright, remember that number. 0. I'm bad at memory. 79 point. Let's add a column to our Excel spreadsheet. Alright? So, let's go back up here. Alright? And let's go zoom enhance. No. Let's right click on our C column at the top. So click on C, then go right click, and we're going to insert, and we're going to insert a column. Thank you very much. Look at that. Okay? Actually, I changed my mind. Control Z. Let's go to F. Right click on F and go insert. Thank you very much. Oh, we're going to have to change. Oh. All right. Let's get rid of our borders. Highlight all your data and go no borders. Now, over here, I'm now going to go watts per square meter. Okay? Which is still intensity. In fact, I'll put it down there. What just happened? All right. Let's just write watts per square meter. Now, what we're going to do, we're going to do some coding, some equations. You're not getting your calculator out. Go into cell F5, which is right next to E5, and you're going to go equals, open bracket. So equals, then shift 9, and you're going to click on that number there. So click on it, and it'll go, do you mean E5? You go, yes, I mean E5. You're then going to go shift 8, and that's the symbol for multiply. And then now we're going to multiply it by our conversion. We're going to convert it to watts per square meter. We're going to pretend our little halogen or incandescent lamp is acting like the sun. 0.0079 close bracket. So I'm saying that in this cell here is that cell times 0.0079. Press enter. 8. Now see, yep, some of you already know. In the bottom right corner is a little green square. When you hover your cursor, it changes from a fat white crosshair to a skinny black crosshair. When it turns to the skinny black crosshair, you're going to click and drag. It's going to take that coding all the way down. Oh dear. It's rounding. So maybe we need some more decimals here. Okay? So, it's taken that, it's saying, all right, we're taking that, timesing it by, to the 0 decimals, it's correct. All right, we need more decimals. So, let's highlight our data again, and let's go more decimals, please. Thank you, that'll do. All right, so yes, obviously these are not just 1, they are 0.65, 0.74, 0.89, etc., etc. Now, let's do the same next to J. I'm going to go right click to J and go insert. Oh, hang on, it's at the end anyway, don't need to. We'll go over here, watts per meter squared. We'll do the same. Equals bracket, that number, times by 0.0079, close bracket. Drag it down. Uh-oh. Same deal. With our medium intensity, it's telling us that you're not getting many watts per square meter. Which makes sense. What's wrong? You good? Shall we go 2 decimal places again? There we go. So, yes, obviously that is not 0, it's 0.244. That is not 1, it's 0.92. Okay, now, let's go back to our nice big thick borders, because good borders make good tables. Thick borders make good fences make good tables. Let's highlight our intensity there. All right, cool. And all right, cool. Now, lastly, you will notice we've added a new column, but this top heading is only over G, H, and I. We want to add J. So this is where we merge and center. Merge and center is my most favorite Excel table feature. So you're going to highlight G, H, and I, and you're going to click merge and center. This is a great way to create a label that spans multiple columns. Thank you, Excel. Click it once, click it twice, boom. Click it once, click it twice, boom. And maybe we could no, thick borders make good. There we go. That's looking good. That's what. Control Z if you want to opt out. And always be saving. I mean, now the new Microsoft. It's frozen. Oh no! You should have it. It's gone. Hopefully you've got autosave on it, right? They discovered that it's just easy to save everything. Now, it's corrupt. Gentlemen, see this graph? I've already done all the hard work, okay? I've highlighted everything, I've added my labels. If you want, you can go up here and add, obviously we want to add our axes titles to both horizontal and vertical axes, but I've done a lot of work, so I don't want to have to do it again. So let's see if I can cheat. See, when you click on your graph, it highlights a pink and purple is saying, I'm plotting that against that. All I'm going to do is drag that across. So move your cursor to the blue, and when you get to the icon that looks like that, it's saying, let's drag that sucker across. Now, it's not going to change the shape of our data because all we've done is multiplied that by 0.0. So all it's going to do is it's going to reduce our y-axis by our conversion factor. So let's drag him across. Oh, thank Christ. There we go, it's done it. Okay, and the way you can check, well, it's not too hard, it's the column's now there, our y-axis now goes up to 9, okay? And our gradient should have probably reduced. Let's do the same for over here. So same deal, we're going to drag that across, boom, cool. Yo.
Times the the average bar to get the watts per meter squared?
What do you times the 0.0079? 0079 with a 0 point in front of it. Okay, cool. So now, we're not going to do it because I don't want to waste the whole lesson, but you're nearly there. You're working through your data and you're about to, you would add your labeled axes. So you go to chart elements. So design, add chart element, primary, blur, add chart element, primary, blur. All right, you would put everything in. Then you just click, copy, paste into Microsoft Word. Quick question. Does anyone teach you this at this school?
No.
What are you in?
In one of our math classes in like year 7 or something.
Okay. See, this is what makes your investigations and your lab reports look really nice. You can still handwrite your tables. You can still handwrite, and in fact, you still have to hand draw graphs, which is a bit unfortunate, but that's because the year 12s that just came out of the physics waste exam an hour ago, they have to hand draw a graph. What I would say to you in an investigation, you could submit that digitally and then still have the piece of graph paper stapled at the back. All right? Now, the argument is that it's actually Microsoft Excel that went to all this hard work to make this beautiful graph correctly plotted with linear scale step, appropriate scale. You're not getting the marks in the marking key. All right, so normally your graph is worth 5 marks, and has he plotted it correctly? Yes. Is this line of best fit correct? Yes. So I would suggest to you include this. All right, it's only going to take you an extra 5 minutes sitting at your laptop to make sure that your graph should look like that. If your graph doesn't, then you've made an error somewhere. So you can use Microsoft Excel to sort of help you make nice graphs. Okay? Now, gentlemen, I set my globe to 12 volts. And I used the same light boxes on the same optics bench with the same lab quests. Well, actually, no, we've got about 12 light boxes, and we've got about 12 lab quests, and we've got about 12 light boxes. But if they're all the same, we should be getting similar data. So for me, I tell a lie. I gave you options. When I said high voltage, you can go 8 to 12. I actually went 12. So I'm just going to go 12 volt globe. Who here went 12 volts? Yeah. Oh. If you've ever given the option, you always go to the maximum setting. Why would you just go to 10 volts? So, all right. So I'm hoping, if this is a reliable experiment, and if that is the pattern, we should all have fairly similar gradients. What's up? Maybe I did this. Now, I did this in the lab prep room where there was a lot of background light. You guys did this where there was a lot of darker. What's your gradient? 0.9. 0.7. 0.5, 0.9. Okay, all right. We can get through this yet. Yes. So right click on your data, and you're going to go down. Right click and go add trend line. Okay, so if you delete it, right click, add trend line, and you're going to select linear, and then the bottom 2 boxes you're going to tick. All right. Oh, now one last thing. There should not be a y-intercept. That means if I went to an infinite distance where r is infinity, then 1 on infinity squared is 0. You should get 0 intensity. So the equation suggests there shouldn't be a y-intercept. It's a little bit close. There's one other option you can do, but we tend not to do it in physics. And that is that you can force your line of best fit to pass through the origin. If you go right-click Format Trend Line, you can set intercept to 0. Oh! Now look what happens. So now it's going, I'm pointing my line of best fit to the origin. Look, the first half of the day is above the line, the next part's below. That is not a line of best fit. It's gotten worse. That is a line of lesser fit. Look what happened to our correlation. It went from 0.996 to 0.97. It's saying, no, buddy. That's not what's going on. We're going to have that. That is the best correlated linear curve, 0.996. Okay? Now, I'm just going to remember, in fact, here's what I'm going to do because I am lazy. I'm going to control cut.
So how do you have the equation?
When you do that.
There's 2 boxes at the bottom of your trend line options. You tick those 2 boxes.
Oh, cheers.
No wuckers. All right. So let's now go to page number 10. Page number 10. Page number 10. Let's just try and tie this exercise up with the next exercise. So, look what I've just... Ooh, looky. I'm going to have to flip this bad boy. Okay, just below that lovely diagram of our increasing surface area sphere, I'd like us to take... work? Okay, I've got a lot to write in this little space down here, so bear with me. Could you just write up here, Joshua, shush. I would like you to write I equals P over 4 pi times 1 on r squared. So all I have done is I've rearranged that equation. That's a 1. It might look like a silly way to express the equation, but that is still technically correct. I could merge these together and you've got P on 4 pi r squared, which is... So all I've done is I've brought the r squared out and given him his own inverse. Okay? And the reason I have done that is because this is now in the form y equals mx. And look what we did. We plotted, believe me, intensity on the y-axis, and then we plotted 1 on r squared on the x-axis, and so that means that our gradient should be the power of our little sun, the light box, divided by 4 pi. So, to get power on its own, I'll just have to multiply by 4 pi. Okay? Now, so what I'm just going to quickly rewrite here is P on 4 pi equals gradient. Therefore, the power equals gradient times 4 pi. So let's take that gradient from our axis and go 0.3196 times 4 pi. Now pi is about 3 and 4 is about 12, 12, 13. 13 times 0.3, that should give us the power of the globe. It's probably not correct, but would somebody mind multiplying my number by 4 pi and shouting the answer out for me? I left my calculator in my pencil case.
4.016.
It's in my locker. 4.02 watts. Okay. Now, wouldn't you know it? No, that's not how they do it. No. You can figure out the power of the sun, but you're taking one measurement. You could go outside with our LabQuest, and we might do this. It's not too tricky. You take the LabQuest out, you set it to lux, you point it at the sun, and you get the intensity, and we're actually at a distance of 150 million kilometers away, which is that. So if you plot 1 on r squared against that intensity, you get one line, and you go, well, if I went to an infinite distance, I'm 0. So you make a line from origin to your one data point, and that's just a way of, you can figure out the power output of the sun. Would you like to do that in tomorrow's lesson? Okay, yes. Cool. And then you could go home and tell your parents that. It's like one of those internet memes, like the question 1 is like, what is 4 times 3? And then question 2 is, Mary has 5 buckets of water, calculate the mass of the sun. Stuff like that. You can actually calculate the mass of the sun. The year 12s have done that a few times in physics, and we're going to calculate the power output, so you can race home and tell your parents. Now, actually, there's a lot of stuff that isn't actually relevant to us right now, but there would be another way. Here's my little candle. Oh no, that's a globe. I don't know. You could measure the current through and the voltage across, and if you multiply current times voltage, it'll actually give you the power. So, but we didn't do that. Gets a little bit too complicated. We've got a voltmeter across the globe and we've got an ammeter, but we could go back and check how much power was that globe putting out, and then we made an assumption. What was the assumption that we made? Yep.
That it's perfectly energy efficient.
No. We pretended that it was acting like something. Yeah, we were pretending that it was acting like a sun. If I did a little bit more research, maybe I could find a website. I kind of almost got there. I'd have to sit down and think about what the heck this thing's doing, because it is a halogen lamp. I don't know the luminous efficacy of lumens per watt. I'm not quite sure why surface area is in feet squared. So, I'd have to... There's more conversions there. I'd have to add more columns to my Excel table. We're not going to do that, okay? So, let's get to today's lesson. How much time have I wasted?
2 minutes. 2 minutes.
Oh, it looks like you guys have some homework. All right, now, here's the deal, yo. I could write power over 4 pi R1 squared equals intensity 1. Okay? You with me? Yeah. I could then say that power equals 4 pi R1 squared times intensity 1. Now, if that is a constant, which it is, your light bulb is sitting there burning brightly, same voltage, same current, same intensity, the power's not changing. All right? Pretending that it's still plugged in and it's just pumping out the same amount of joules per second. So if that's constant, then watch what we can do. We can have a little trick here. I could say that 4 pi 1 R1 squared... Oh, there's no 1 with pi. What am I doing? R1 times I1 equals a constant, which could then equal 4 pi R2 squared times I2. We could change the distance, and that's what you did. You changed the distance and you saw the intensity change. You increase R, I goes down. Now, this is just a nice mathematical equation. Let's cancel out the common stuff. Get rid of 4 pi, get rid of 4 pi, get rid of the constant. We're left with 4 terms. So look what we get. We get R1 squared on R2 squared equals I2 over I1. And this is an equation that I'd like you to write down, put it in a box, highlight it, because it's very, very useful. And this will go in your second test, and you'll have to use it. Okay? Now, it's a simple ratio, so there's no units here. You've got meters squared over meters squared equals watts per square meter over watts per square meter. It doesn't really mean much to us. It's just a ratio. But what's important here is its inverse, so you notice that the 2's are on the other side of the fraction. So if I2 goes up, R2 goes down, and it's an inverse square. Okay? So, let's just use this. Maybe we could just watch a Michael Vsauce video for the... Yeah. We'll do all of this worky tomorrow. Yes. All right. The intensity of sound, let's just do one example. R1 equals 2. I1 equals 1 watt per square... In fact, 1 watt per square meter is enough to turn your eardrums into a bloody pulp. So it's probably not... Me talking right now, I'm putting out about a microwatt per square meter. Not much energy. All right, so I probably should have changed that. What is I2 per square meter when you're 6 meters away? Now, we could look at this using the diagram above. We're going from R to 3R. I've tripled my distance. So if I've tripled my distance, then it should be a 1 over 3 squared. We should be getting a ninth of the intensity. And so if I just times 1 by 1/9, that is the answer. But here's what you want to do. We're going to throw our equation down. Or let's just make you guys good students. Let's write all of our variables down. R1 equals 2. R2 equals question mark. No, it's not. It's 6. I1 equals 1. I2 equals question mark. Now, when you get these kinds of equations, you obviously want to rearrange for I2. Oh look, I2 is already at the top. That's great. But normally, if you flip one side, you have to flip the other. So we might get to a scenario where you just have to flip both sides, get the subject on its own. So let's just write the equation down. I2 on I1 equals R1 squared on R2 squared times both sides by I1. And then throw the values in. So that's 4 on 36, which you will notice as 1/9, and then the inverse of 1.11111, I think, 0.111 watts per square meter. Okay. So obviously these were nice round numbers, and so we could have done the mental maths. If you triple your distance, you get a 9. It's not always going to be nice round numbers. You might be 2.5 meters away and the intensity is 3.67, and then you go to 4.34 meters. You go, right? You can't just do mental maths. You've got to use the equations. Okay? All right, I've spoken for too long. Kenneth's probably getting a bit tired with his earbuds in watching this, so let's stop the video there. Kenneth, we're going to watch a Vsauce video. I'm not sure what, so sorry about that.